still in section 10.1, and we're going to be talking today about power in a little while. But for right now, we need to look at graphs in terms of the force and the distance moved. So you might have a force and distance graph that looks something like this. This is distance, and distance will be measured in what unit?
Meters.
Meters. And we have force, which would be measured in newtons. Okay, so we know that if you're actually calculating work, you do force times distance, right? As long as the force and the distance are in the same direction. So in terms of a graph, if there is a constant force, it would look something like this. Pretend that's horizontal. Okay, so it would be a constant force. Let's say that this was 50 newtons. And let's say that this thing is moving along, and right at this point, here's 0, and it has gone 10 meters. All right, so if this is the force is constant at 50, and it goes for 10 meters. We have a force, we have a distance, they're in the same direction, so you can just multiply them, and that comes out to be the area under this graph. Okay? So our work equals force times distance, and in terms of graphing, it's the area under the curve.
We can do this on the calculator.
Yeah.
Yeah.
Is it like Simpson's rule? How about that?
Don't think so.
Well, I mean, like, you can do it on a calculator and you graph the area under the curve, right?
Oh, can you? Okay. Yeah. I don't know how to do that yet.
Oh, it's actually very simple.
It's very simple? Okay. So I just would have to, that's a skill I just have to make myself learn. But for right now, there you go. Now, if the force is changing, that helps too. Now the force is still can still be in the same direction, but having a changing magnitude. So we could have another one, force times distance, or force times displacement. Displacement in meters, force in newtons. Again. But if it's a diagonal, that means it's a constantly changing force. Okay, so let's say up here, right about here, we have 30 newtons. And down here we have 5 meters. Okay, we can't just take 30 times 5 because the force isn't constant. Okay, the force isn't constant, but we can still use that strategy that we used before about area under a curve. So what we can do is we can drop down our imaginary line here, and we're going to look for the area of this triangle to be the work. So the work will be equal the area under the curve again. Of an F force displacement graph. So work equals the area under the curve on an FD graph. And so in this case, area of a triangle is 1/2 base times height, right? So it's 1/2. What's the base of this triangle? 5. Good. And the height is 30. So 15 times 5, which is 75. Okay, so here's our answer. What's the unit for this if this is the work?
You in trouble today. Newtons? No.
Newton.
Joules.
Meters.
Meters.
Newton meters, or kilogram meters per second. Okay, so 75 Newton meters, which is also the same as saying 75 joules. You were right. Because that's the unit for work. Okay, everybody got that? So area under the curve will give you that if you happen to be given a graph. Now we're going to move on to a new topic. We're going to move into power.
God bless you. God bless you.
Okay, and power is actually the rate of doing work. Rate of doing work. Write this down. Okay, what else can you think of that were rates?
Ratio.
Not, well, ratios kind of, but what else, what other rates have we studied this year?
Rate of doing work.
What? Efficiency?
Yes.
Kilogram meters per
We
second.
actually haven't gotten to efficiency yet.
Kilograms meters per second.
Speed, velocity, good. That's a rate of, it's a rate of travel, okay? Meters per second. You could have a rate of change of speed, which is acceleration.
That's too much.
So it's something over a unit of time. So it's a rate of doing work. So that means how much work can be done in every unit of time. Power equals work divided by time. Work divided by time. Work is measured in what? Joules. And time is measured in seconds. So one way of thinking about power is in a joule, as joules per second. But there's another unit for this, and this is where it gets sometimes confuses people. But power is measured in what we call watts.
What?
No.
What? Yeah, watts.
What?
Your thing.
So watts is with a W. That's the unit for power. Work is with a W. But W in the equation stands for the unit that is measured in joules, and P in the equation is the one that's measured in watts. So you need to make sure that you get that straight. So it's a unit called watts. Now another thing that's a little sideline that I just want to mention. You know how work is very closely related to energy? You know how work is very closely related to energy? Another way to think about this is just a sidebar, but I want to make sure I mention it. Power also is energy divided by time. Okay, energy use divided by time. We think about this type of power more when we're thinking about electricity. It's still joules per second. You can measure how much energy is going through a light bulb per unit time. That's what that unit, when you have a 60 watt bulb, it's 60 joules every second is going through that bulb. Okay? Now this work has to do with actual motion, because energy can be used for different things. Energy can be used to produce light, which is where you mostly have heard of watts. But energy can also be used to cause a change in motion, which is what we talk about when we have the work here. Okay, so work per unit time. So we need to get some examples of that.
Okay.
Let's get an example question.
Great example question. You stop.
What's your great example question, Damon?
That's a good one.
Let's get a great example.
Why you never handsome young man?
Okay, so we're going to do a problem for the power equation now. An electric motor can raise an elevator 18 meters in 30 seconds. If the elevator has a mass of 200 kilograms, what power does the motor produce to lift it? It's got to have the power in order to lift it. We know we have the equation. P equals work over time, right? Because we're trying to but we're trying to figure this out. We have to do a little bit first. Okay, the time isn't the issue. We have the time. But what is it that we still have to calculate in order to use this? The work. And what's the equation for work?
Force times distance.
Force times distance. We have a distance. The distance is not the issue, but what's our issue?
We don't know the work.
We don't know the work. What else don't we know? The force. We know the time. The time says 30 seconds. We don't know the force, but we have something that we can use to find the force, and what's that something?
Mass.
Mass. So what would be my equation to use to find the force? Good. The force is 200 times 9.8. Should be what? Let's get a calculator here.
Like 19 something. Yeah, I got it.
Maybe it's 1960.
1968.
Come on. Come on.
Yep. We'll just prove it to you. 1960. What's our unit?
Newtons.
Newtons. Okay. Now we have to backtrack and use that in this equation. So work equals 1960 times
18.
18. That's our distance. So our work is going to be 1960 times 18. 35,280.
Joules.
Good. 35,280 joules. But we're not done yet.
Oh, now we gotta put that in the P.
Now we got to use that in the power equation. So power equals 35,280 divided by
30.
30.
Oh.
30 seconds. 1176.
Watts.
Good.
Oh.
1,176 watts. So we finally came up with the answer, but you have to be familiar enough with your equations that you make the question actually easy. The lifting questions, a lot of times you'll have to find the force first, but if they give you the force first, don't multiply, never multiply the Newton part by 9.8. Look and be careful as far as what they're giving you. Use the units to help you figure it out. This is a mass, so you did have to change it. You did have to figure out the force, but if they give you the newtons, then don't worry about it. We have 4 practice problems after that, 9, 10, 11, and 12, that use the same thing. They have different missing pieces. So what I want you to do is work on those right now.
Let's go.